Welcome back. Today we're tearing right into one of the absolute highest stakes, most complex decisions in modern aerospace, choosing a rocket. It's this massive, fascinating puzzle of physics, economics, and engineering, where hundreds of millions of dollars are literally on the line. By the end of this explainer, you're going to see exactly how the experts actually make it happen. Now look, if you think picking a rocket is just about finding the absolute biggest explosion to lift the heaviest object into the sky, well, you're definitely not alone. It's a super common misconception. But the reality? Launch vehicle selection is absolutely not based solely on payload mass. There is a whole universe of interrelated factors at play here. Think of it kind of like this. How do you choose a vehicle for a highly complex, incredibly expensive road trip? You wouldn't take a massive tractor-trailer just to pick up groceries, right? And you definitely wouldn't use a two-seater sports car to move a family of 6 across the country. Aerospace engineers face a very similar, albeit much more explosive, dilemma. So how do they actually decide which rocket gets the job? Okay, let's dive into this roadmap. We'll start with 1, the ultimate space ride, move to 2, 8 crucial selection factors, then 3, classifying our launch vehicles, 4, real-world rocket examples, 5, the step-by-step selection process, and wrap up with 6, why vehicle selection matters. Section 1, the ultimate space ride. What are we actually trying to achieve here? At the end of the day, the primary objective is straightforward. Deliver that payload safely, reliably, and economically to its destination. But to do that, an optimum launch vehicle has to check a ton of boxes. We're talking delivering the payload to the desired orbit, ensuring total safety, maximizing capability, minimizing cost, and hitting the schedule. On top of all of that, it has to be perfectly compatible with the spacecraft itself, while providing just enough performance margin so you aren't sweating the whole way up. It is an incredible balancing act. Which brings us to Section 2, 8 crucial selection factors. Let's look at what makes this balancing act so delicate. Now, what's really interesting about this slide is how wildly different payloads dictate entirely different vehicle classes. Mass is foundational for sure. If you're launching a small satellite, you only need a small ride. But if you're launching a massive space station, a heavy comm satellite, or an interplanetary spacecraft, you're going to require medium to heavy lift vehicles to handle not just the satellite, but the payload adapters, protective covers, the whole shebang. But hey, knowing what you're lifting is only half the battle. You have to know exactly where it's going. Low Earth orbit, or LEO, is great for Earth observation and crewed flights. Sun synchronous orbit, SSO, is perfect for environmental monitoring. But for TV and communication satellites, you're going to need the much higher altitudes of geostationary transfer orbits and geostationary Earth orbits, GTO and GEO. That orbital altitude, the inclination, and the injection accuracy strongly dictate your rocket choice. And it doesn't stop there. Engineers must consider a slew of additional factors. Mission requirements, like crewed versus cargo, change everything. Launch site location is huge. Did you know sites closer to the equator actually give you a free velocity boost just from the Earth's rotation? You also have to weigh vehicle reliability based on historical success rates, total launch cost, schedule availability, and spacecraft compatibility, making sure the physical and electrical interfaces match up perfectly. All right, let's step onto the showroom floor. Section 3, classifying our launch vehicles. Engineers classify these rockets strictly by the payload capacity they can carry to orbit. So we've got small launch vehicles handling up to 2 tons, medium launch vehicles cover that 2 to 20 ton sweet spot, then you step up to heavy launch vehicles, taking on those massive 20 to 50 ton payloads. And then there's the super heavy class, above 50 tons. Take a second to just appreciate the sheer scale of that. These are the absolute behemoths, modern heavy lifters designed for the most demanding space road trips imaginable, like deep space probes or heavy lunar and Mars missions. Let's move on and see how this builds into reality. Section 4, real-world rocket examples. This is where we see different countries highly optimizing vehicles for their specific strategic jobs. Take India's PSLV. It's an absolute workhorse for Earth observation, while their GSLV Mk3 steps up for heavier comms and human spaceflight. The USA's Falcon 9, of course, is legendary for commercial and ISS missions. Over in Europe, the Ariane 6 handles commercial GEO satellites. China relies heavily on their Long March series, and Russia's Soyuz has this incredibly long history of crewed and cargo missions. These aren't generic rockets, they are highly specialized tools. So we know the factors, we've seen the showroom, let's get into the workflow. Section 5. The step-by-step selection process. Now, traditionally in the source literature, this can be a grueling 8-step process, but systems engineers generally boil it down to this clean 4-step logical flow to guarantee a match. Step 1. Define the mission and exact payload characteristics. Step 2. Pinpoint the target orbit and estimate your launch energy. Step 3. Compare your options, strictly weighing historical reliability against total cost. And Step 4. Assess compatibility, checking dimensions, environments, separation systems, and finally, lock in your vehicle. And remember, while they're doing this, aerospace engineers are running extremely rigorous technical and cost-benefit analyses. They're obsessing over structural safety margins, verifying exact propulsion capabilities, checking guidance and control systems for orbital injection accuracy, and mapping out environmental constraints. They are literally doing everything possible to eliminate mission risk. Let's bring it all together now. Section 6. Why vehicle selection matters. So the crucial point here is that proper selection shapes the very future of commercial spaceflight. Making this highly multidisciplinary decision correctly maximizes your payload capability and minimizes your launch risk and cost. It supports future scalability. Because let's face it, getting this process down to a science is exactly what enables today's reusable vehicles, epic rideshare opportunities, and rapid launch availability. We've seen that picking a rocket is a masterful balancing act of mass, orbit, reliability, and cost. But as space gets increasingly commercialized and as massive rideshares and reusable rockets become the new normal, I want to leave you with this. How will this highly structured engineering process have to adapt? What will the ultimate space vehicle selection look like tomorrow? Thank you for exploring this explainer with me,